And welcome back, College Algebra class. We are now in Chapter 5, Section 7, Complex Zeros and the Fundamental Theorem of Algebra. This is the last section in Chapter 5 that we were dealing with in our course. So we'll dive right in here. Our objectives, we're going to use the conjugate pairs theorem. We're going to find polynomial functions with specified zeros and find complex zeros of a polynomial function. Sounds like a lot of fancy words. Let's dive into it and see what we end up with. So by definition, our complex zeros, it says a variable in the complex number system is referred to as a complex variable. All right. And a complex polynomial function of degree n is a function of the form here. F of x is a sub n x to the n plus a sub n minus 1, x to n minus 1, etc. Now, we have taken a look at this item before. We've seen this equation. We've seen this equation when we were working with polynomial functions that had real zeros. And that's actually identical to the polynomial function with real zeros. So what changes? What changes is that in these, we're saying that our coefficients here, our a sub n's, a sub n minus 1's, all the way down to a sub 0, are now complex numbers. So if we have our numbers, our coefficients, and our constant are complex, then we have a complex polynomial function, and then we're going to end up with complex zeros. So instead of f of r equaling 0, meaning that r is a real zero of the function, now we're saying r is a complex zero of the function because we're dealing with complex numbers. So just a quick review of complex numbers here, since this is what we're dealing with. Typically, they look like this, a plus bi, where a and b are both real numbers. So we have a and b are real numbers, and I, of course, is our imaginary value, where I squared equals -1, or the square root of -1 is I. So again, that's imaginary because that really doesn't make much sense. If something's squared, negative times a negative should be positive. So if we get a negative, we say that's our imaginary component. So if we have our complex numbers off to the side here, just take a look at a couple scenarios. If a equals 0, then a plus bi is just bi. So we could say oftentimes that this is the pure imaginary number. So 1i, 2i, 5i, -8pi, or -8i, etc. We could also say, so what if b equals 0? Then a plus bi is just a. And so if our imaginary component disappears and a is just a real number to begin with, that really is all of our real numbers. So all of our real numbers and all of our pure imaginary numbers are subsets then of our complex number system. So all of our complex numbers are made up of these a's and these bi's. Now, if in this case a is not equal to 0 and b is not equal to 0, then of course we just have kind of the traditional complex number a plus bi in this case. All right, so that's just a quick what we have worked with previously in all of these. What we have seen before is that our b term was 0. So we had a plus 0 i's, or just a, and that worked with only our real numbers. Now we're letting b be something different, some other number, so now we end up with complex numbers. So one of the items that comes out of this then is the fundamental theorem of algebra. So an item that's beyond the scope of our class, something that we're not going to prove for our class, but we can at least take a look at. It says every complex polynomial function of degree bigger than or equal to 1 has at least one complex zero. Okay, so we're going to end up with at least one complex zero overall. So what does that complex zero look like? Well, that complex zero could look like just a, it could look like bi, or it could look like a plus bi. If we have degree 1 or more, we have to have a solution that looks like one of these. Absolutely has to happen. That's what our fundamental theorem of algebra is talking about in this particular case. Additionally then, several theorems in here, then we'll get into some calculations. Every complex polynomial function of degree greater than or equal to 1 can be factored. Okay, so we can factor all these into n linear factors, not necessarily distinct, meaning we could have something that repeats. So if I would have x minus 1 squared, I could rewrite this as x minus 1 times x minus 1. So we're saying these are two factors, not necessarily distinct, those are the same factor, but it's listed twice. But x minus 1 quantity squared written in linear format is just x minus 1 times x minus 1. Linear format means that the exponent on our variable is 1. Okay, so we can rewrite these all down a little bit further. What we had said previously when we had not complex polynomial functions, but just real polynomial functions, that we could rewrite in factored form as far as linear functions along with unreducible quadratic functions. So now what we'll find out is that the unreducible quadratic functions end up giving us then our complex values, or our items that end up looking like the a plus bi. So let's take a look at that. So we're going to end up, in this case, using the conjugate pairs theorem. We don't quite know what that theorem is yet. It's down here at the bottom of the page. We're going to look at that here in a moment. I want to use this just to set this up. So if we find the zeros of the following, so if we take a look at f of x is x squared plus 1, we can say, all right, well, when does x squared plus 1 equal 0? Now, graphically, when we take a look at that, x squared is a quadratic. Plus 1 means it shifts up 1. So here's the graph that we have, okay? And it touches the y-axis at 1. And we can take a look at this and say this then has no real zeros because it doesn't cross the axis. Remember, the definition of a 0 is what's the value of the function that makes it equal to 0. In this case, there's no x that does that. If we solve it algebraically, though, so if we take a look algebraically, we have x squared plus 1 equals 0. We can subtract 1 from both sides, so that x squared is negative 1. To get rid of the square, we will square root. So that gives us x equals plus or minus, because we're in the equation, we have to consider the principal and non-principal roots. So the square root of negative 1, that is how we defined I. So we end up with our solutions here. We have complex solutions where a is 0. So if I write this in a plus bi format, that would be 0 plus or minus 1i. So a is 0 and b is 1 in this particular case. So we do satisfy then, we do satisfy the fundamental theorem of algebra where we have at least one complex 0. Okay, in this case we have, instead of a plus bi, we have bi, but we have two of those. Okay, the theorem says we have to have at least one. So we can have more, but we have to have at least one. Okay, so that's part of our idea. And then the conjugate pairs theorem here. Notice pairs. If we have a pair of something, that means we have two of them. So notice when we have our solution here, it's positive I and it's negative I, because in the equation we consider the principal square root and the non-principal square root. So we always consider the positive as well as the negative. So the positive is 1, the negative is a second, or maybe instead of saying 1, it should say first. So the first and then the second, so then we have a pair of items. That leads us then quite naturally into the conjugate pairs theorem. Suppose that f is a polynomial function whose coefficients are real numbers. So what we've been looking at, if r equals a plus bi is a real 0 of f, then its conjugate, r bar with a line over, so r bar is a minus bi. So our conjugates are going to be a plus and a minus. So the other traditional way to write this is we have a plus or minus bi. So why plus or minus? Because we get the I by taking a square root. When we take the square root, we consider the positive, the plus, as well as the negative, the minus. So anytime we have one imaginary number, we'll always end up with its opposite. Okay? Always, always, always. And that's what we're illustrating. So the conjugate pairs theorem was illustrated then up here in this example. So we had plus I and as well as minus I. So positive I and negative I are complements of each other. Okay, and so the complement is just, we have the digits here, one with a plus between them and one with a minus between them. That gives us our complements. So corollary, we have not talked too much about that in our course this semester, but as we take a look at corollaries are something that follows quite naturally after a theorem without a whole lot of additional thought or strain, if you want to think about it that way. And the corollary says that a polynomial function of odd degree with real coefficients will always have at least one real zero. Now, if we think about the end behavior of odd functions, that's what I've got listed here. The ends have to go to positive and negative infinity. So if I've got an odd function, the definition of odd function, at least as far as the end behavior, means, or the characteristic of an odd function, is that the ends do opposite things. If we had an even function, the ends would do the same things. Odds do opposites. So if I have just a grid in through here, and I've got one side that has to go to negative infinity, the other side has to go to positive infinity, and this is a function. Now, since this is a polynomial function, very specifically, polynomial functions have to be smooth functions when we draw them, as well as continuous, meaning there's no gap. So how can I get from negative infinity to positive infinity without touching every single value in between? Which means then I had to cross the x-axis somewhere. Wherever I cross it is a zero of the function, and that would be a real zero of the function. We can graph, for our purposes, we only graph real numbers. So we're not graphing complex numbers, so if we cross the x-axis, then we've got a real zero, and we have to have at least one of those. We may end up with more, but we always must have at least one if we're an odd function, because we have to go from negative infinity to positive infinity. Now, if I have an odd function that's going the other direction, maybe it starts at positive infinity, goes down to negative infinity. Same idea. I could have some other terms and stuff in here, do some other funky stuff along the way, but overall, I still have to end up crossing the x-axis somewhere, at least one spot. And so that gives me at least one real zero. That is the corollary to the conjugate pairs theorem. Take a look at another example here. Let's use the conjugate pairs theorem. Let's say we have a polynomial function f of degree 5, whose coefficients are real numbers, and has the zeros of 1. Let's go ahead and highlight this. Zeros of 1, we have a 0 of 5i, and we have a 0 of 1 plus I. So we were just given 3 specific zeros. Our dilemma here is in our question, we were told we have 5. When we go back and we take a look at our fundamental theorem of algebra, actually not that one, that's the one that says if we have at least degree bigger than or equal to 1, we have one complex 0. Okay, there was another theorem right after that. Let's come back up here just a minute and come up here. This theorem here, let's start this one. Every complex polynomial of degree bigger than or equal to 1 can be factored into n linear factors. So if it's degree 5, can be factored into 5 linear factors. Degree 10 can be factored into 10 linear factors. So if we're taking a look at degree 5 down here, that means then that we should be able to list 5 linear factors. We've got 3. So our question comes in, where's the other 2? Okay. So the other 2 come in with the conjugate pairs theorem. So the conjugate pairs theorem is that whatever complex number I have, I also have its conjugate. So if I have over here, I've got 1 plus 0i, that would mean then that 1 minus 0i would technically be a value as well, but 0i is just going to be 1, so it's 1 plus 0i or 1 minus 0i is redundant, means the same thing, so really nothing to see there. If I have 5i, that means minus 5i is also a solution, because it would be 0 plus 5i, 0 minus 5i. Well, these values are different, contrary to that first column here. And typically, we don't write the zeros in front if we don't need to, so we just have 5i. But we just figured out our other, or one of our other zeros, one of our other zeros is minus 5i. Additionally, if I have 1 plus I, that means I also have to have its conjugate 1 minus I. Well, that's different than what's written first, so I have my second remaining 0. So in this case, what we were asked to do was just find the other remaining zeros. So the shortcut of this is to ignore the constant, just take a look at the expressions that have i's in them, okay? Because in this constant, yes, I'm going to have 0i. Let's look at my screen back here, a little technical glitch. There we go. So we've got a 0i and a minus 0i. That just doesn't mean anything. So it's just 1. And so we're only going to write that as 1. We're going to write the 5i as 5i instead of 0 plus 5i. And then the minus 5i, instead of 0 minus 5i, we'll just write minus 5i. And the 1 plus I, we'll have to say is 1 plus I, and then the 1 minus I. So what I'm getting at here, not trying to beat a dead horses, take a look at the I items, so the items involving I, those are the ones that we also have to make sure we have its opposite. So if I would have had a 1 minus I to start with, then 1 plus I would have been its conjugate. If I would have a minus 5I to start with, plus 5i would have been its conjugate. So we've answered our question here. The remaining two zeros are these two here. It's negative 5i and then 1 minus I. Some of our homework is just going to ask us to do that. Can we come up with the other zeros? If we have conjugates, then we know, or if I have complex numbers, I know I also have to have their conjugate as well. So how do we use these? One of the things that we can do, objective 2 here, find the polynomial function with specified zeros. So now what if we're given the zeros and we want to figure out, well, what was the original function? Most of what we've worked up till now is here's a function. Let's go ahead and find what the zeros are of the function. Now we're reversing it. We're saying, okay, what if I have the zeros? Can I come up with the function? So for example number 2, find a polynomial function of degree 4. Okay, so that's important. If degree 4, that means we must have then 4 zeros. Okay, must have 4 zeros. Complex, so you got to have 4 complex zeros. Coefficients are real numbers that has zeros of 1, 1. So we got a double root here, double 0. Okay, so graphically, what that would mean then is at 1, the graph would have had to turn. So it's either going to turn that way, or at 1, it would have turned this way. Not exactly sure how it's turning, but we know it's got to turn there. And then we've got negative 4 plus I. Now, since this is written in the a plus bi format, we also have to have its conjugate. So the conjugate would have to be negative 4 minus I. So take this exact same item and only change the i's value. So if it's positive, change to negative. If it's negative, switch to positive. That negative 4 in front, we leave alone, and we don't have to do anything else with it. So here's what we end up doing next then. Now we can say that f of x is going to be some leading value that we can multiply through, multiplied by x minus a root, in this case 1, x minus the next root, in this case another 1, x minus, and then we've got negative 4 plus I, multiplied by the next root, x minus negative 4 minus I. So as we multiply this through, I would have x times x, which is x squared, times x, which is x cubed, times x, which is x to the 4th, and I could have some leading coefficient in front of that. If we're not told anything else, we just assume that that's going to be a, for just a lack of a variable to use. Okay, so when we went back up to our definitions, notice that, and this is what I'm emphasizing here, this a sub n. So I've got some value out front I can multiply by, don't know what exactly it is, so for lack of a better descriptor, we'll just go ahead and use a, so just a generic value in front. All right, and now that we have this, well, our goal then is to multiply all this out and see what we end up with. So this is going to be a little tedious, so we have to be slow and careful here, not try to rush too quickly. So we got a, we got x minus 1 times x minus 1. So that would be, let's see, x. So if what I'm going to end up doing here, just for sake of example, I'm going to group the first 2 items together, and I'm going to group the next 2 factors, which you could say factors together. So we got x times x is x squared, x times minus 1 is minus x, minus 1 times x is another minus x, minus 1 times minus 1, or negative 1 times negative 1 is positive 1. Let's take a look at what we have next. So a couple of things we can do on this one, and just as personal preference. Let me show you a technique here that is kind of nice, and then if we happen to see it and use it, and then I'll show you how we can modify this if you don't happen to see the technique and what we can do. So what I'm going to do is I'm going to just distribute the minus sign through both of these sets of parentheses. So I've got x plus 4 minus I, then we've got x plus 4 plus I. So here's where the interesting piece comes in. Take a look at what's here in the green. I have an x plus 4 and another x plus 4. So I can say this is x plus 4 kind of grouped together minus I, and then x plus 4 grouped together plus I. So if I take a look at those just as they sit, what we end up with is the format of a minus b, rather, that's how I've got it written. A minus b times a plus b, where a happens to be x plus 4 and b is the I. Well, this is the special format of conjugate pairs. Conjugate pairs always give us the difference of squares. So what I end up with here with the conjugate pairs, if I multiply this out, I'll end up with a times a is a squared, a times b is ab, then minus b times a is minus ab, then minus b times b is negative b squared. The middle terms cancel out, and we end up with a difference of squares. What's nice about this is since b is I, this will end up as I squared. We know that has a value of positive 1. So we can shortcut some of our steps here if I happen to recognize that sequence. So let's go ahead and do that. Let's recognize the sequence here. So the left part of this I can still simplify. So minus x is minus 2x plus 1. And of course we still have all of this out here. So as we continue here, x squared minus 2x plus 1. And then from our green pieces in here, this green box, what I have is I'm going to end up with x plus 4 squared minus I squared. So this other piece over here still stays the same. So we've got a, x squared minus 2x plus 1. And then this other piece over here, x plus 4 quantity squared, is going to follow a set pattern. If I have a plus b squared, that holds true. That's always the pattern of a squared plus 2ab plus b squared. Okay, just to double check, a plus b times a plus b would be a times a is a squared, a times b is ab. B times a is another ab, hence we get 2 of those, and then b times b is b squared. So when I combine these two, I get those the same way. Okay, so we're going to use that in this technique here. So it's square the first term, so x squared. Okay, that's what we end up with. So square the first term, multiply the terms together and double it. So x times 4 is 4x, doubled makes 8x, and then we end up with b squared. So b in this case is 4, so that's going to end up being 16. Then we also have the minus I squared, but I squared is 1, so we end up with minus 1. All of that then to get us down to our next line. So we have a times x squared minus 2x plus 1 multiplied by, let's see here, we've got x squared, and I've got plus 8x, and then I've got plus 15. So what I've got it down now is a constant times a trinomial times another trinomial. I still need to multiply all these out because the question is asking for a polynomial function of degree 4 with these zeros. So it's really asking for me to keep on going and to finish this out. So as we finish this out, I may need a little bit more space here. Let's see what we end up with. So I know I'm going to have the a out front. Okay. Now what I'm going to do is I'm going to go ahead and start grouping these a little bit more and lining these terms up. So let's see. I've got x. Now when I multiply trinomials times trinomials, I could do it vertically. I'm going to do it horizontally in this case. But the idea is same with when we have binomials, as I want to take each term in the parentheses, multiply it by each term in the next set. That's the distributive property. So x squared times x squared is x to the 4th. X squared times 8x is 8x cubed. X squared times 15 is 15x squared. Now I'm going to multiply the minus 2x. So let me go ahead and color coordinate this a little bit. So that's minus 2x multiplied by x squared is negative 2x cubed. So I'm going to line that up in a cubed column here. Negative 2x times 8x is minus 16x squared. Negative 2x times 15 is negative 30x. Now I'm going to multiply it by the 1. That becomes easier because it's just this whole thing written down. So x squared, going to put that in the x squared column, and then plus 8x, and then plus 15. So I don't quite need this to be so large as far as over here, so let me do it this way. Now we can combine like terms. So what do you end up with? I got a in the front, some multiplier, and then I got x to the fourth. Let's see, our x cubed term is going to be plus 6x cubed. Our x squared terms, I got 15, and one is 16, minus 16, so my x squared terms are going to end up disappearing. Then I have minus 22x, and then a plus 15. Okay. And as I do that, one of the things I happen to look up and glance and notice, I made a minor mistake up on this line up here. So hopefully you caught that. Minor mistake, but it is a mistake and is going to affect some of our work here. I squared is negative 1. I forgot this is minus I squared. So it's minus negative 1. So instead of 16 minus 1, it becomes 16 plus 1, which is 17. So I need to change this 15 here to a 17. So that's going to change one line or one item in each of these three lines. So let's go back through and double check and fix those. Okay. So if we happen to notice it, obviously let's go back and fix it here. So let's see. So when I multiply by the x squared, it ended up being 17x squared. So I got to fix this one. It's going to be 17x squared. Negative 2x times 17, instead of being negative 30, it's going to be negative 34. And then 1 times 17 is going to end up being 17. So let's go back and readjust down through here. Hopefully you found this mistake before I did. So let's see, so I got x to the fourth, then I've got plus 6x cubed, and plus 17, and 1 is 18 minus 16 is 2. So I'm going to end up with 2x squareds. Negative 34 and 8 is negative 26x. And then I have the plus 17. Finally, that is our polynomial function. Now, what this illustrates in part is when we're doing this on the homework. When we're doing this in homework, this is going to be a little bit tedious when we put this in the online homework because I made a single mistake up here. I forgot a negative. What that did then is it changed all three of these resulting terms, which then changed the coefficients down here. That poses problems in the computer because the computer will only count it as correct or incorrect. We would have to go ahead and then go back through our work. I would encourage you not just to go ahead and just start retyping things. Go back, double check your work, see if you made that same mistake I did. Okay, did not do that on purpose. Wish I could have said, oh, I planned that mistake so that it represents or to illustrate the notion, but I did not. It is just a simple mistake, but we go back and we correct those. Okay, so that does answer the question. One of the things I had said earlier, though, was that when we were up on this step up here, okay, we might have seen that we had this pattern as far as conjugate pairs. If we happen to see that, great. If not, let's go ahead and take a look at what this would have become otherwise. We would have had x plus 4 minus I multiplied by x plus 4 plus I. At this point, we would have to distribute this. So as we distribute, we would have had x times x is x squared, x times 4 is 4x, and then we have x times I, which is ix. Then I multiply the 4 through. So again, let's try to color coordinate this a little bit. So multiply the 4 through. So we got plus 4x, then we got plus 16, just plus 16. So I don't have a column for that yet. Then we have a plus 4i. So we'll put that one out there. And then we also need the minus I. So we got minus ix. So I'll line that one up. And then a minus 4i. So I'll line that one up. and then a minus I squared. So I don't have any I squareds in here, so put that one over here. Now let's combine things. So I've got x squared, we've got an 8x, the ix terms go to 0. I've got a 16. The I terms here go to 0. I got now I'm hopefully not going to make this mistake here. Minus I squared. So minus -1. That gives me x squared plus 8x. That's a double negative, so that means positive. So that's plus 17. Hopefully you see here x squared plus 8x plus 17. X squared plus 8x plus 17, we do end up getting at that point that same result. So it really doesn't matter if you happen to see that the pieces over here are conjugate pairs, which then lead to difference of squares, or if you just go ahead and multiply them out and you get there by brute force. Okay. Oftentimes when I'm working on these, if I'm lecturing in person to a class, I will, the first thing I do just by nature is I just brute force it. I don't know, maybe it says something about my personality, I'm not sure. But I just go ahead and multiply it out and end up with this piece down here at the bottom right away. And then I've got it over here. Okay, so that is just a different technique that we can use, and it just depends on what you're comfortable with. Okay, doesn't matter in the end which way you do it. We just got to do it one of those ways. Okay, so let's move on to our last objective here. Our last objective is to find the complex zeros of a polynomial function. So in our previous section, in section 5.6, I believe it was, so we're in section 5.7 at the moment. In 5.6, we did find zeros of polynomial functions, and they were all the real zeros. Now we're expanding this out, and the only change is now we're replacing real zeros with complex zeros. So all the other basic requirements still hold true, it's just now we get to go ahead and use our complex items. So as we continue here, let's take a look at our function. We got f of x is 3x to the fourth plus 5x cubed, 25x squared, plus 45x minus 18. First thing we do is we notice that we've got it in standard form, and we got decreasing order, and 4 is our degree. That means then that we can write this with 4 linear factors. Okay, so we want to go ahead and be able to find some of these items. Okay, now one of the things we can still go back to is Descartes' rule of signs. Okay, figure out how many real zeros we can end up with, and we'll end up with our complex along the way as well. And I think one of the last examples we did in section 5.6 basically covered this same idea. So this is a bit of a repeat here. Not a bad idea to go ahead and repeat some material. The more exposures we get to something, the better off we are at remembering, the easier it is to remember. So if I take Descartes' rule of signs, let's see, I go from 3 to 5, they're both positive, 5 to 25, both positive, 25 to 45, both positive, 45 to negative 18, I've got one sign change here. So I could end up with 1 or 0 positive real solutions. Or instead of solutions, I could say what we've been working with, we could end up with zeros because we don't have the set to anything. So we'll call it a 0. That's the correct term here. Now, the other thing we want to figure out then is what if we have f of negative x? So if we take this whole thing and plug negative x in for all the x's, remember the even exponents will go ahead and stay as is because negative x to the power of 4 is going to be negative x times negative x times negative x times negative x. 4 negatives are going to become positive, and it's still going to be x to the fourth. So multiply by 3 then is still 3x to the fourth. The odd ones here change signs. So we end up with negative 5x cubed. We have 25x squared minus 45x. We're going to change signs, and then the minus 18. So as we take a look then at our sign change, they go from 3 to negative 5. So there's a sign change. Negative 5 to positive 25. There's a sign change. Positive 25 to negative 45. There's a sign change. Negative 45 to negative 18, no sign change. So what that tells us, and we get 3 sign changes, so we end up with 3, 1, or 0 negative real zeros. Okay, so at least we know that. We know we've got either 1, 0 or positive, 3, 1 or 0 negatives along the way. Now let's take a look at the possibilities for our zeros. So this is the rational zeros property. And so our possible zeros, okay, remember our factors of our last term, our constant, divided by factors of our first term, our leading coefficient. So we want then factors of negative 18 over factors of positive 3. So let's take a look at that. So because we have potential for positive and negative solutions, we'll consider the positives and negatives. So let's see, I could have 1 and 18. So also, excuse me, 1 and negative 18 or negative 1 and positive 18. So in effect, I end up with positive and negative 18. Additionally then, I have 2 and 9. So it's going to be positive 2 and positive 9. Let's see, 3 times 6 is 18. So we got positive 3, positive 6, and that's the end of those. Whoops. Trying to clean up here, and my hand moved and got it all over the place. And then factors of 3, well, we could do plus or minus 1 and plus or minus 3, because I got 1 times 3, or I could do negative 1 times negative 3. As we reduce all of these, what are the possible zeros? And we got 1 over 1, which is 1. 2 over 1 is 2. 3 over 1 is 3. We can see then we're going to end up with 6 over 1 is 6. 9 over 1 is 9. 18 over 1 is 18. Now let's put them over 3. So plus or minus 1/3. And then plus or minus 2/3. Plus or minus 3/3, which is the same as 1, so I already have that one. And then 6 over 3 is 2, already have that one. 9 over 3 is 3, already have that one. 18 over 3 is 6, already have that one. So these are all the potential zeros. So these are all the things then, if we have real zeros, those are the real zeros that we could come up with. So if these are all the zeros that we could come up with, what is our next step? Now we actually go through and we do our synthetic division, and we take a look and see, well, which ones actually end up being solutions. Let's see. So in our original function here, 3x to the 4th plus 5x cubed plus 25x squared plus 45x minus 18. Let's go ahead and pull this off to the side. Let's pull out the coefficients. So again, make sure when we're doing synthetic division, and there is another video in our coursework here in Canvas that does go back over synthetic division. So if you're a little rusty on the synthetic division, please go back and reference that video as well, and that will review the synthetic division. So what we do is make sure that we're not missing any terms. So the power of 4, 3, 2, 1, and then power of 0. So all we do is we take the numbers here. So we got 3, 5, 25, 45, negative 18. And then we go ahead and we say, all right, well, these are the possible zeros we end up with. What we're going to do then is we're going to start trying things until we find something that works. Now, the good news is we have a limited number of items to try. Bad news is that these limited numbers are still 2, 4, 6, 8, 10, 12, 14, 16 different items. So it's possible that we could end up going a ways before we end up finding all the solutions. Just one of the things that happens, okay? So let's see. If we plug 1 in here, so synthetic division, we bring our first number down, multiply then our number in the bottom row times what's in our box. That's 3. Write it in the next row. Add these together. So it's a series of adds and multiplies, okay? 8 times 1 is 8. Add these together, we get 33. 33 times 1 is 33. Add these together, we get 78. 78 times 1 is 78. When we put this together, this is definitely not 0. So that is not a solution. So let's go ahead and try negative 1. So we got 3, 5, 25, 45, negative 18. And let's see, bring the 3 down. 3 times 1 is negative 3. Add those as 2. 2 times negative 1 is negative 2. Add those, we get 23. Multiply again, we get negative 23. Add these together, we end up with 22. Multiply that together, and we end up with negative 22. When we put those together, that's not 0 either, so we know that that's not going to be a solution. Now, if we want to be a little more technical, let's see, this top one here to be 60. That's not 0, so it's not a solution. This one here is negative 40. That's not 0, so that's not a solution. So we know that 1 and negative 1, neither one work. Let's go ahead and move on to 2. So we still have 3, 5, 25, 45, and negative 18. So we got 3. 3 times 2 is 6. 5 and 6 make 11. 2 times 11 is 22. Add these together, we get 47. That becomes 94. As we add these together, that's going to be 139. And as we take a look at this, is definitely going to be a not 18. So I'm not even going to finish that one. We can if you want to. Doesn't work. Not going to worry about that one. Let's go ahead and try negative 2. So we got 3, 5, 25, 45, negative 18. Bring the 3 down. 3 times negative 2 is negative 6. It's negative 1. See, that becomes positive 2. So that's 27. It's going to be negative 54. Just reverse numbers here. But in any event, that's going to end up being negative 9 there. Yeah, negative 9. And negative 2 times negative, hey, there we go. It's positive 18. So when we go ahead and subtract, or excuse me, add these together, that gets 0. That means then, this is what we were looking for. Since that's 0, this must be a 0. So negative 2 goes in, or x minus negative 2 goes into the function evenly. So that means that as a factor, we know we've got x minus negative 2. So there's at least one factor. And then this is another factor. So if we started out with factor of 4, then this would be 3x cubed minus x squared plus 27x minus 9. Okay, and so that's what that would end up being. And so we could rewrite this as x plus 2 multiplied by 3x cubed minus x squared plus 27x minus 9. And that would at least start us on our way. Now, a couple of things we can do. Here's the thing where it gets kind of interesting. It's a matter of personal preference and choice as far as what you want to take a look at from here. We can either keep on going and seeing what else we can find, okay? Because we did find one real negative solution, right? Okay, so let's go ahead and come back up through here. So we have found one negative real solution. So we found at least one. So either there's going to be 2 more or no more, okay? And so that's at least where we stand at the moment. The other thing that we can do, so at least recognize there could be another negative, so we still have some other things that we can try. We can come back up through here, see if negative 2 is a repeat factor, then we can do plus or minus 3, plus or minus 6, plus or minus 9, etc., all the way through. Now, the other thing that we can do as we work on these is we can see as we get going, do any of these depressed polynomials? So that's what this is called, if you remember from synthetic division. Depressed polynomials are always 1 less than what we started with. So if this up here represented 3x to the 4th, 3x cubed, etc., and then this really would have been x minus negative 2. So we're dividing by an x to the 1st, so 3x to the 4th divided by x to the 1st is 3x cubed. So since this is always a power of 1, then this depressed polynomial is always 1 less than what we started with. One way to remember that's the depressed polynomial is if you're always 1 less than everybody else, you might be just a little depressed also. Okay, trying to find a way to make sense of that. I'm not trying to make light of any mental illness or anything, but just recognizing mnemonics and ways to try to memorize what's what. Okay, now if I take a look at trying to do this just by factoring, since I have 4 terms here, I would take a look at factor by grouping. So I would say, okay, what do these first 2 have in common? They both have an x squared. So I'm going to factor an x squared out of those, and I get a 3x minus 1. Take a look at these 2. They both have a 9 in common. So I can say that's 3x minus 1. Since in that when I do factor by grouping, if what's inside these parentheses is the same, then I can finish this out and it will factor by grouping. If it did not factor by grouping, then I would have to go back to this synthetic division technique and keep on going by brute force until I could find something else that worked. Okay, so as we keep this up here, let's see what we have. So I still have the x plus 2 out front. Then I have the 3x minus 1. If I take the 3x minus 1 out, I'm left with an x squared from this first group, and I'm left with a plus 9 from the second group. Now, as we keep this going a little bit further, let's see. So what we were trying to do was find the complex zeros of the function. Okay, so what we have is we've got x plus 2 could be 0 because we got it in factored form now. 3x minus 1 could be 0. And x squared plus 9 could be 0. So that was the overall goal that we were trying to find. We were trying to figure out what the zeros were. That means in my factored form, I just set it equal to 0. So on each one of these lines, I could have said equals 0. Now that I've got it factored by the zero product property, each of these factors can be set equal to 0. So let's see, as I solve this, I subtract 2 from both sides. So one of my zeros is negative 2. Well, no big surprise. That's what we had found out up here, was it not? Okay, so that's what we anticipated. This other expression, if I solve this, I would add 1 to both sides, so get 3x equals 1. And if I divide by 3 on both sides, then I end up with x equals 1/3. So now I have one negative real solution. I have one positive real solution. If I go back to what I had seen previously, then I have, okay, by Descartes' rule of signs, I'm going to end up with, since I know I now have one positive real zeros, there are no more positive real zeros. Okay, so that none else can occur. So I only have one. I could end up potentially with 2 other negatives. Okay, if I end up with 2 negatives, then I end up with 3 negatives, and then 1 positive gives me my 4 zeros, which is a possibility. Okay, let's take a look at other things that happen. Oh, the other thing, if we take a look at our possibilities, we had up here negative 2, and now we have, what do we just figure out? Positive 1/3. So way back over here. So if I would have been doing this by brute force, close to the end is where I would have figured out that this was a factor. Okay, or a solution, or a zero, or a root. Okay, so that would have taken me some time. So if we can figure out to factor this along the way, makes things go a lot faster. Okay, now let's finish out this last one, x squared plus 9. So I can say x squared equals negative 9. See here, if we take our square roots on both sides, I end up with x equals plus or minus the square root of a negative. Square root of 9 is going to be 3. Square root of the negative is going to be 3i. So now I end up with my imaginary or my complex solutions. So overall, the solutions here, what we were asked to do is find the complex zeros. That was the original set of directions, find the complex zeros. So our complex zeros are negative 2, 1/3, 3i, and negative 3i. This down here at the end is our answer to what that question was asking. Okay, so if we go back up to the top here, we say, okay, here was our original question, find the complex zeros. So we use some of the things that we had from our last section with Descartes' rule of signs, some of our other theorems, and then we figure out what our complex zeros are. So we found the zeros. Again, one of the things we like to do in mathematics is reverse things. So what if we go ahead and take a look at this item at the top of the page, top of the screen. Information is given about a polynomial f of x whose coefficients are real numbers. Let's find the remaining zeros of f. So since I know it's degree 4, I've got to have 4 complex solutions. So since I have I have to have its complement, got to be negative I. Since I have negative 4 plus I also have to have its complement, so that's got to be negative 4 minus I. Guess what? As opposed to that last question that took us a lot of brute force, this one's really quick. Okay, this one just asks us to find the remaining zeros. The reason I put this question and the next one is these are questions from the homework as far as our material in my math lab, and so I wanted to show you a different way that these could look. The last thing then, last example here for section 5.7 is to form a polynomial function f of x with real coefficients having the given degree and zeros. So that really looks like one of the examples that we had previously, only it gets a little bit longer. Okay, so just wanted to go ahead and put this out here to at least do the setup to see how do we go ahead and put these together. And I went ahead and listed the answer here. So let's see, I've got zeros of -5, negative I. Well, if I got negative I, that means I also have to have positive I. Because 7 plus I, which means I also have to have 7 minus I. So now I've got 1, 2, 3, 4, 5 zeros. Now I know what all my zeros are. I wasn't given all of them directly. I had to go ahead and do the conjugates to figure out what they were. Okay. Now that I know them, I can write them in factored form. So f of x is a. Notice in our expression, a is going to be listed for us in our homework. So that's kind of a nice item. Then I'm going to end up with, let's see, x minus -5, because remember, it's if r is a root or a 0, then x minus r is one of our factors. So I have x minus -5. We got x minus -I. We also then have x minus positive I. Then I'll have x minus 7 plus I. Remember, put these in parentheses because we're subtracting the entire root here. Then we have x minus 7 minus I. Now what we have is we just have a lot of distributive property to deal with. So as we multiply this through, I end up with x plus 5. Then over here I've got, let's go ahead and simplify this, x plus I times x minus I. And I've got x minus 7 minus I, just distribute that minus through, distribute this minus through on this side as well, minus 7 plus I. Now we end up, if we just finish this out, we've got a, and then x plus 5. Now over here we've got conjugate pairs, so I'm going to end up with x, let's do it this way. Let's group these two together. So it's going to be square of the first term, which is x squared. So that's going to be x squared. And then I'm going to end up with minus ix plus ix, which goes to 0 ix's. Then I got I times minus I is minus I squared. Let's make sure it's a minus I squared. Now let's take these over here together. Okay? And as we do those, one of the things that I would do is I would multiply this out just with brute force here. So as we take a look at this, this would end up being, as I start multiplying, I'm going to have x times x, which is x squared. And I got minus 7x, and I got plus ix. Then I've got, let's see, let's do this in orange here. Minus 7 times x is another minus 7x. And minus 7 times minus 7 is positive 49. Minus 7 times I is minus 7i. Let's use the red color here. I got i's in here, so minus I times x is minus ix. Then we got a plus 7i, so line those up. Then I got a minus I squared. So now let's keep on going here. So I've got a is going to be x plus 5 multiplied by x squared. So I squared is -1, so the negative of -1 is plus 1. Then let's see, then we've got x squared, we've got minus 14x, the ix's cancel out, the i's cancel out, I squared is going to be -1, so it's going to be minus -1, so that's going to be plus 1. Plus 1 and 49 make 50. Okay, caught that from earlier, remember I had a mistake from earlier in the video. Okay, so now that we have this, now it's multiplying all of this out. What we should end up with then is what's up here in that box. Okay, so if you just want to fast forward the video, that's where we're heading. If you want to hang on for the whole thing, we'll see what we end up with. So f of x then is a multiplied by, so let's distribute this, x times x squared is x cubed. We got plus x. We got a plus 5x squared. We got a plus 5. Okay, so I'm just going to go ahead and reverse these. So I've got a plus 5x squared, and then the plus x. That way they're in descending order. Then I want to multiply that by x squared minus 14x plus 50. So I still have this a out front, so that just stays out there. Let's go ahead and start multiplying. So x cubed times x squared is x to the 5th. X cubed times minus 14x is minus 14x to the 4th. X cubed times 50 is 50x cubed. Again, let's start color coordinating these. Let's do the minus 5x squared times x squared is 5x to the 4th. So align those up in the x to the 4th column. 5x squared times minus 14x is going to be an x cubed. See, 5 times 10 is 50. 5 times 4 is 20. 50 and 40 is 70. And that's negative. So we've got negative 70x cubed. And let's see, so that's 5x squared times that 50. That's going to be 250x squared. Let's multiply the x through. X times x squared is x cubed. X times minus 14x is, we got minus 14x squared. X times 50 is 50x. And finally, let's multiply by the plus 5. So that's going to be 5x squared. 5 times minus 14, we said was minus 70. So it's minus 70x now in this case. And 5 times 50 is 250. Let's combine all these terms together. See if we end up with what we believe it ought to be. Let's see, combine it. I like to go ahead when I expand trinomials and things large in trinomials, I like to go ahead and write this a little bit bigger, use a little bit more space. That way everything lines up. So I got x to the 5th. I've got a minus 9x to the 4th. Let's see, we got 50 and minus 20 is, minus 70 is minus 20. So minus 19x cubed. Let's see, I've got a 250, 255, minus 14. 255 minus 14, let's call it 241x squared. That's going to be a minus 20x. And then we have the 250. Wrap that up. Okay, so here's what we have. Cross our fingers that this was indeed what we had at the beginning. Because in this case, again, this was a homework question. I copied the answer also. And so we see, in this case, thankfully, everything does work out. And so that's a question style, at least, you will end up seeing in the homework. Okay, so that wraps up for us all of Chapter 5. This is actually the last section, 5-7, complex zeros and the fundamental theorem of algebra. And so what we're able to do now is we can find the zeros, not just all the real zeros. Now we can also find the complex zeros. And given complex zeros, we can also now reverse and come back to and find the function that would go ahead and give us that. Okay, so fascinating how, I think it's fascinating how we can come forwards in mathematics, then we reverse it and we get our items going one way, and then we get our items going the other way. All right, so as I've said before in our videos, that wraps this one up. If you've noticed a mistake, please go ahead and let me know so I can fix it. If you're one of my students in College Algebra, I'll see you in another video. And so that's it. Take care. Bye-bye.